In exam 2, one of the multiple choice questions asked you to determine which of the following molecules is or are polar. They gave you the Lewis structures here, so the first thing we're going to do is turn those into molecular geometries. In the case of BF3, our steric number is 3 because there are 3 atoms bound. Lone pairs, 0, meaning that we're in a trigonal planar geometry. In the case of COF2, the steric number is 3, and the lone pairs are still 0 because you got 3 atoms bound, meaning that this one is also trigonal planar. Now in the case of PCl3, our steric number is 4, and our lone pair is 1. 3 atoms bound, 1 lone pair, steric number of 4, meaning that we are in a trigonal pyramidal geometry. And finally, we've got our PCl5. Steric number in this case is 5. There are 5 atoms bound to the central atom, no lone pairs, so we're in a trigonal bipyramidal geometry. So now that we know what the shape of these molecules are, the next thing we should check for are polar bonds. We need to do our delta chi check. So in the case of boron-fluorine bonds, you're looking at 4.0 for the fluorine minus 2.0 for the boron, which equals 2.0. So these are polar bonds. There's a chance that we have a polar molecule. In the case of COF2, for the carbon-oxygen bond, that's going to be 3.5 for the oxygen minus 2.1 for the carbon equals 1.4. That's a polar bond. In the case of the carbon-fluorine bond, you're going to have 4.0 for the fluorine minus 2.1 for the carbon. That equals 1.9. That's also polar. But notice, the differences are, the delta chi's are different. That will have an effect on our answer. Let's take a look at the phosphorus chloride. And that's going to work for both of these. You've got 3.0 for the chlorine minus 2.1 for the phosphorus, giving us an overall delta chi of 0.9. These are still polar, so all of these are still candidates to be polar molecules. We need to draw in our molecular dipoles. So for a trigonal planar species like BF3, all of the bonds are in the plane of the paper. There's a 120-degree bond angle. If we draw in our dipoles, it's going to point from the less electronegative atom to the more. These are all going to cancel out because they're pointing in completely different directions and they're the same size. So no molecular dipole due to symmetry. Let's draw our COF2. And we're going to draw in the magnitude, kind of our dipoles. So the CO bond had the smaller dipole, and this one, the CF, both had larger delta chi's. So these two have a component that's pulling all of the electron density this way, and that overwhelms the carbon-oxygen bond dipole. So this one has a dipole, and it's due to the asymmetry. In the case of PCl3, we're in that trigonal pyramidal geometry, so we've got the lone pair sitting in the plane of the paper, we've got one chlorine sitting in the plane of the paper, then one coming out and one going in. We're going to draw in some dipoles because these bonds are polar, and then we've got a big dipole here with that lone pair of electrons. So here, these dipoles are going to add up to something that's not just canceling each other out because of the asymmetry. So this one also has a permanent dipole, and it's due to that asymmetry. Finally, the PCl5. Let's draw our three-dimensional structure of that. You're going to have 3 of the chlorines sitting in the plane of the paper because we're in the trigonal bipyramidal geometry, and you've got one going out and one going in. If we draw in our dipoles, geometrically, Since these are all the same size and they're all pointing in different directions, they're going to completely cancel each other out. So we've got no overall dipole moment due to symmetry. Our middle two options are the only polar molecules.